Okay, so here we are with our video to learn how to do mole conversions. In your packet, there's a worksheet that you can use to take notes as we go along. There is a place for you to do a mole map right at the top, and this is going to be kind of our explanation of how to do these conversions and the numbers we're going to use, the relationships we're going to use to do those conversions. You'll notice I have moles here in the middle because moles really are the central unit in chemistry. My chemistry teacher years ago told me, when in doubt, change it to moles and see what happens. And that advice has served me really well. So we're going to start with our conversion between moles and particles, which actually you saw a little bit of in the video and the reading that you just did. The idea here is to be able to convert back and forth, to be able to go from moles to particles, and then also to go from particles to moles. And so when we do our conversions, in order to do that, we're going to be able to use Avogadro's number. And you'll remember Avogadro's number is 6.022, my 2's look weird, 22 times 10 to the 23rd of something, anything, doesn't matter what it is. And so when we're using Avogadro's number, you'll remember particles, if we're dealing with elements, that means atoms. And if we're dealing with compounds, that means molecules. So when we're dealing with particles of any type, that's going to be our atoms and molecules. We're going to be using 6.022 times 10 to the 23rd. Now, the next thing that we're going to have to do is moles to mass. This one is probably, definitely the most common conversion that we need to do. And so we do this conversion quite a bit. So we're going to be going from mass back and forth, mass to moles, and moles to mass. And when we do that conversion, we're going to be using something called molar mass to do that. The molar mass of something is the mass of 1 mole, and we find it by using the masses from the periodic table. And you'll see the definition underneath your box for the mole map. And you'll notice it also says there, always round the table mass to 2 decimal places. So we're going to practice those in just a minute, and we'll get down there to do those. And then the very last thing we're going to do is the conversion to volume. And so when we are going back and forth to volume, this is a very specific instance. When we are going to volume, we are just going to right now be working with the volume of gases. Whoops. My stuff is moving around here. Volume of, I'm getting caught, a gas. I can't write all of a sudden. At STP. And STP stands for standard temperature and pressure. And it really is not a big deal that you know what that means at this point. We'll get into more details with standard temperature and pressure when we get to our gas laws unit in Unit 6. For right now, we're going to assume that everything that we deal with gases is at standard temperature and pressure. And when it is, we use what we call molar volume, which is 22.4 liters of gas at STP. It absolutely does not matter what gas we're talking about. If you remember, Avogadro had said that equal amounts of a gas, equal volumes of gas at same temperature and pressure would have the same number of particles. And that volume for 1 mole of particles is 22.4 liters. So these are the conversions we'll be using. Now, let's talk a little bit about molar mass. And go to the molar mass stuff. So you notice there's a definition down there, mass of 1 mole of a substance. We're going to use the values from the periodic table to determine and calculate molar mass. If you remember from the last thing you watched, the little video from TED Ed, they talked about 18.01 grams of water being 1 mole. And I asked you the question at the end about where that 18.01 grams per mole comes from. And really what that is a molar mass. So it's very, very simple. The first example you have on your paper is oxygen. And if you remember oxygen from biology class, whenever you write it in an equation, it's O2. Oxygen is diatomic. We're going to get to that in just a second. So when we have O2, that means we have 2 oxygens. So we're going to take 2 times the mass of oxygen from the periodic table, which is 16.00. Remember, we're always going to have these 2 decimal places here. And so when we do that, we end up with, for our molar mass, so we end up, I don't know what happened there. So we end up with our molar mass of 32.00, and our units are going to be grams per mole, because this is the mass of 1 mole of something. So we're going to do the same thing when we have carbon dioxide. Our next example, carbon dioxide, of course, we all know the formula is CO2. And so I would have 12.01 is the mass of carbon from the table, 2 times the mass of oxygen, which is 16.00. And when I add all of that up, I'm going to get 44.01 grams per mole. Very simple. And then the last one in your example is calcium nitrate. Calcium is Ca, nitrate is NO3. Whoops, that doesn't click at 3. There we go. And there are 2 of them. So I have, remember the distributive property here is going to affect how many of each of those I have. So my mass of calcium, when I do this, so the mass of calcium is 40.08, and there's 1 of those. I will have 2 times the mass of nitrogen, which is 14.01. And I will have 6 times the mass of oxygen, which of course is 16.00. And when I add all of that up, I should get 164.10, and that's in grams per mole. So that's how we're going to calculate our molar mass. Now, if you flip to the back side of your paper, you'll see there are several problems for us to work through. Now, there are a couple of things I want you to remember when you're working through these. We're going to be using factor label problem method solving stuff to do this. So we're going to have keep our units straight, make sure that we're using the proper labels. I'm going to talk about that as we go along. So the first one we're going to do is a moles to grams, so moles to mass problem. So you're always going to start by writing down your given information. So we're doing how many moles are there in 75.1 grams of carbon. You'll notice that when I do my units, I've done grams C. Now, it seems a little tedious at this juncture to be doing that, but you will see as we get into more and more complex problems where we're starting with one thing and ending with another, it becomes very helpful in your problem solving to make sure that you're labeling not just the unit of measurement, but what it is that you're measuring. So I'm going to start with my 75.1 grams of carbon, and in order to go from grams to moles, if you look at your mole map, you'll remember that grams to moles is going to be my molar mass. And so I want to put grams at the bottom here because I want to get rid of and cancel my grams of carbon. And I'm going to end up with moles of carbon, which is what my problem is asking me for. So for every 1 mole of carbon, I look at the periodic table and I find that I have 12.01 grams of carbon. And so then I can simply do 75.1 divided by 12.01 and I get 6.25 moles of carbon. Now, you'll notice a couple of things here. When I did this, I rounded to 3 significant figures because that's what I have here. Generally, your molar mass has 4 or 5 significant figures to it and really should not be used to limit the significant figures in your problem. So always come back to what you started with when you're determining your significant digits. All right, so our next problem, we're going to go the other way. I'm starting with 8.2 moles of magnesium, and so I'm going to start by writing down my given information, 8.2 moles of magnesium. You'll notice that the abbreviation for mole, I keep doing that, I don't know if I said it anywhere, is just MOL. I don't know, it shortens it by a letter. I guess if you write it enough, it matters. But so we have 8.2 moles of magnesium. Excuse me, we're going to go to grams. So again, I want moles to be at the bottom because that's what I want to cancel. Grams of magnesium is what's going to be up here on the top. And so for every 1 mole of magnesium, excuse me, you look at the periodic table and you have 24.31 grams of magnesium. And so then when I do my my math, I'm going to do 8.2 times this 24.31, and what I'm going to end up with is like 199 point something on the calculator. But when I look back at my 2 sig figs, I'm going to have to round that 199 to 200. But I want to make sure that this one is significant, so I'm going to put a line over it. And of course, my units are going to be grams of mg. So our next problem, we're going to do something a little different. This time we're starting with atoms and we're going to moles. And so as soon as you see atoms to moles, you should be thinking Avogadro's number. So if I start with 8.95 times 10 to the 27th, and that's atoms, there's really no abbreviation for that, and we're dealing with boron. And when I do my conversion, I'm going to start with atoms down here on the bottom because I want that to cancel. So I have atoms of boron down here, and I'm trying to get moles of boron up here on the top. And I know for every 1 mole of boron, I have 6.022 times 10 to the 23rd atoms. Avogadro's number, right? And so when I do the math, and I punch this into my calculator, I should find I get like 14,862, but I want 3 sig figs, so I'm going to round that to 14,900 moles of boron. Something. The next problem on your sheet is changing moles to liters. And so again, I'm going to start with my 5.6 moles. And this time, I have carbon dioxide, but really, it doesn't matter what gas it is, because anytime you're doing volume at STP, it's going to be the same conversion no matter what gas you use. So my moles of carbon dioxide, I want to cancel, are going to go down here. For every 1 mole of carbon dioxide, I have my molar volume, 22.4 liters of carbon dioxide, or any other gas for that matter. And of course, then my moles are going to cancel. Liters will be my units. When I do my math, I find that I have, I get like 125 point something, but I need only 2 sig figs. So I'm going to round that to 130 liters of CO2. Whoa, and then my last problem here, second to the last problem. This is where things are going to get a little bit more involved, because we're going to have to do a 2-step problem. Notice we're at molecules, and so that's our particle designation on our mole map, but we're trying to get to mass. There is no way to go directly from molecules to mass, so we're going to have to go through moles in between. And this is what I was saying in the beginning about that central part of all of these problems being moles. So I'm going to again start with my given information. I have 7.43 times 10 to the 22nd, and this is molecules of nitrogen gas. And if you remember, nitrogen gas is going to be N2. It is a diatomic gas, and so we're going to have to deal with that when we get to the molar mass. So molecules first, though, because I've got to get us to moles. So I have molecules of N2 gas. For every 1 mole of N2, I have 6.022. I'm having problems here. 6.022 times 10 to the 23rd molecules of N2. But but I'm not where I need to be yet. My molecules have canceled, but I'm still at moles. And so I need to do one more problem here. And so I'm going to set up another conversion, and this time I'm going to cancel out my moles of N2 and change it to grams of N2, which is what my problem is asking me for. And for every 1 mole, remember it's N2, so I'm going to take 2 times the molar mass, which is 28.0. Whoops. I am having problems here. 28.02 grams. And so when I punch this into the calculator, I'm going to take my 7.43, I'm going to divide by 7.43 times 10 to the 22nd, divide by 6.022 times 10 to the 23rd, and multiply by 28.02. And if I did my math right, I got 3.46 grams of N2. And that, of course, is rounded to 3 significant figures because that's what I started with. Okay, and this one finally is really our last problem. I'm starting again 76.2 liters and trying to get to grams. So again, I'm going to have to do a 2-step problem. So I'm going to start with my 76.2 liters of nitrogen dioxide. So that's NO2. And the first conversion I'm going to do is going to take me liters to moles of NO2. So when I do my liters of NO2 to moles, for every 1 mole, I have 22.4 liters of gas at STP. I'm still not where I want to be, so I'm going to do another conversion. For every 1 mole of NO2, I need to find grams of NO2. And so I'm going to do the molar mass. So if you remember, the molar mass is going to be 14.01 plus 2 times 16.00. And when I do this addition problem, what I end up with is 46.01 grams of NO2. And so I'm going to take that 46.01, I'm going to multiply it by 76.2, I'm going to divide by 22.4, I'm going to round it to 3 significant figures since that's what we started with, and I got 157 grams of NO2. So there's your first setup, your first try at doing some mole conversions. Your next worksheet in your packet is a whole bunch of mole conversions for you to practice, and so I want you to work on those. You will find the answer key on Schoology, so you can check your answers as you go along. And again, remember that there is a discussion post in Schoology for you to post any questions, and I'll get back to you as soon as I can. Hopefully this was helpful.